Hello everyone. In this video we are going to talk about one of the most commonly used algorithms in optimization called the steepest descent or gradient descent. And this is an unconstrained optimization, means that you're only basically maximizing or minimizing a cost function, but it is not subjected to any constraints. Okay, so you are going to minimize and or maximize really a function, right? Of course, when you're trying to use in the negative, as we are talking about it, when you're trying to go in the negative, that's why we call it steepest descent. So when you are doing descent, we are really minimizing. If we are trying to maximize, then we move in the direction of the steepest ascent. Then you can what? Maximize. Okay, so the reason we are saying minimize or maximize is based on how we are moving in this direction from the starting point. But you know, optimization is not just minimizing a function, you can also maximize a function. So if you want to maximize a function, then all you need to do in this algorithm I'll show you is to change a sign. Then you can maximize your function, and then you might call it the steepest ascent. Okay, anyways, you are moving in the positive or negative of the gradient of the function. So first thing first is, what is gradient? I assume you all know it from calculus, but just want to make sure. So a gradient is like the multi-dimensional version of the derivative, right? So if you have a function with a single derivative, f of x, let's say equals to, for example, x squared, right? And then if somebody says what is f prime at 1, you say it's the derivative of this function calculated at 0.1, right? So if the derivative is 2x, then it is going to be 2 times 1 equals 2. And graphically it means what? It means this is the slope of the tangent line. So if you can draw your parabola fx equal x squared at 0.1, if you draw a tangent line, the slope of this tangent line, which is the tangent of this angle alpha, it is equal to what? It is equal to 2 units, right? So this is 0.1 and 1, and this function is y equal x squared, right? That's the meaning of derivative, the slope of the tangent line. Now for a multi-dimensional function, the gradient is going to be the partial derivatives of the function with respect to independent variable, and you write it as a vector. So let's say if you have a function f of x and y now, and you might call it z, let's say, this z, which is a function of x and y, it is, for example, equal to x squared plus y cubed plus 2xy. Right? Now, if somebody says, what is the derivative of this function at a specific point, let's say 1 and 1, then you have to calculate the derivative of z with respect to x, partial derivative, and then partial derivative of z with respect to y, right? With respect to x, you will get 2x plus 2y. With respect to y, you will get 3y squared plus 2x. Correct? Now, if you combine these into a vector, you call that vector gradient of this function f. If somebody says, what is it at 0.1 and 1? You say, well, I form a vector from these two derivatives, correct? And I calculate these derivatives at 0.1 and 1. So if you plug in 1 and 1 for x and y, you will get a 4 and you will get a 5. And now the question is, what does this 4 and 5 vector have to do with the surface that belongs to this three-dimensional function z equals x squared plus y cubed plus 2xy? So here I use the surf command in MATLAB and generated the surface for you. And I also overlaid on the top of that the point 1, 1, and 4 using a black sphere. So that's the point. This is the surface. And if you want, we can go ahead and rotate it so you have a better idea of how the surface would look like, correct? So now the question is, let me see if I can get a nice view and then copy that for you into Microsoft OneNote so you can see it better. Maybe. Just trying to see if there is any good view. Probably something like this. Okay, so let's see if we can copy it somewhere here. So this is the surface of the function. That is the point of interest. Now this vector 4 and 5 means what? So if you move on this surface in different directions from this point 1, 1, and 4, depending on which direction you are moving, the magnitude of your function can what? Increase or decrease, correct? So you see, for example, let me use a different color for you. If you move in the direction of these vectors in red, for example, your function is increasing, and if you move, let's say, in the direction of these vectors in light blue, your function is decreasing. Now the question is, along which one of these directions, if you move, your function decrease is the maximum or your function increase is the maximum? And the answer is gradient. Gradient direction will tell you the direction of the maximum ascent or increase, and negative of gradient will tell you what? The direction of maximum descent or decrease, right? So this is negative del f at 1 and 1, this vector here in black, and this other vector is positive del f at 1 and 1. Right? One of them shows the fastest way to go up on the function. The other one shows the fastest way to go down on the function. Okay? That's what we mean by gradient and steepest or fastest descent and ascent. And there is mathematical proof why this gradient, which is a generalized derivative, will provide you the fastest uphill or downhill direction. So here, since the goal is to minimize the function, we should go downhill, and so we should move in the what? In the negative gradient direction. So basically, if I am at point 1 and 1, what's my next point going to be? So what I need to do here is move in the negative gradient direction from my current point, move in this direction. Let's say this is the negative gradient at that point. And I end up with the next point. And then when I get to the next point, I need to re-evaluate the steepest descent again. Because as you move on the surface, this vector gradient does change from point to point. You clearly see it is a function of x and y. So when you move from one x and y to another x and y, it does change. So you should not keep moving in the original negative gradient direction forever. Once you move a little bit, then you have to re-evaluate. Now probably your negative gradient has changed a little bit, and when you get to the new point again, you re-evaluate it one more time and one more time and one more time until you get to a stationary point, which is your global minimum. In the global minimum, the gradient is going to be 0. It doesn't matter in which direction locally you move from that point. The function is not going to increase or it's not going to decrease. It is definitely going to increase if it's a global or local minimum, but it's not going to go down any further. So negative gradient will be 0. That's what we call an extremum or a stationary point here. And that means you have reached your what? You have reached your global minimum, okay? So you have to continuously update your negative gradient at any point and move in the direction provided by that by a specific amount, which, by the way, this amount that we move in the direction of negative gradient in each step of the optimization, we call it the step size. Okay, here in our algorithm, as we're going to discuss in a second, that is shown by this parameter A. Okay, so this parameter A, or the step size, is something that you have to choose. Sometimes you can analytically calculate what's the best step size to take, and we'll talk more about the step size, but just want to tell you that the terminology for it is called step size. Good. Now let's go back here. So what do we do? Let's say I'm given a function like this, for example, and I can pick up a starting point, any that I want. Let's say here this function has this kind of contour plot. If you plot, let's say call this z, if you plot z versus x1 and x2, the contour plot of that is a bunch of concentric ellipses. And you start at any point that you want. Let's say here, this is the start point. And then you calculate what? The negative gradient. So here it gives you this direction. You move so much in that direction, get to the next point. At this point, reevaluate the negative gradient. Now it is this direction. You move so much in that direction. And then again, at the new point x2, you move so much in the new direction, and keep going until you get to what? You get to the minimum of the function, right? And when you get to the minimum, that's where your gradient is going to be 0, this guy here. And so your update equation, as we're going to discuss, is not going to change the value of x. So if you see the value of x is not changing anymore, that is, or changing very, very negligibly, that's an indication that you have converged somewhere. Okay, hopefully where you converge is what you want, the global minimum. Sometimes you might converge to other points that we'll discuss, and those are the problems or the issues with the steepest descent. But the idea is, if you keep going downhill in the fastest direction that you can, ideally you should get to the bottom of the hill, right? That's the whole idea of steepest descent. So what do we do? As I said, we have a function. Then at any point we move by an amount called step size. Here we show it parameter A in the negative gradient direction, and keep what? Keep updating our x values. Okay, so what does that mean? Let's discuss. So first thing first, let me fix this. Seems like there is a typo. There are two fx's for some reason. So if my current point is vector x, here you see I use bold font. If this vector x, which in this case, let's say in this example, includes x1 and x2, so here this means your x1 and x2. What I do from my current point, I move with an amount of step size in the negative gradient direction, and that gives me the new point z. So z here is like new x. So for example, I can say this x is x at the current iteration, right? Because this is an iterative algorithm, right? This is numerical analysis. This is a loop that you have to keep repeating until you converge. So if x is the current point, this z is like what? The next point. So this is like x1 at the next loop, next iteration of the loop. Something like this. Okay? So that's the meaning of this x and z, current location and next location of the optimizer, or optimizer particle you might call it. And the matter of fact is, definitely the location of the next point is going to be what? A function of the step size, right? Because if x is a known number, let's say here I start at 0.2 and 3, so this is 0.2 and 3, and del f at x is also a known vector, so like the example we just solved, like 4 and 5, something like that, right? So both of these are numbers, x and del f x, but a is a parameter, and so z is going to be the function of that parameter, right? So how far you move along this negative gradient and where do you end up, it depends on the choice of step size. If you use a smaller step size, instead of going from x0 to x1 and ending up here, you might just end up here for x1, right? If I choose half a step size, correct? If I choose again half a step size in the same x1, so at this x1 now that I ended up, there is a contour, and that contour looks like this. So now at that contour, I have to basically do another normal, and that will probably make me go, let's say, in this direction. And then I end up here at another, so it end up with a different path. Typically, the smaller the step size I choose, the more iteration it takes, because you are taking smaller steps. It takes you more time to converge to the global minimum. The good thing about it is you are being careful, you are being conservative, because there are sometimes several issues or several problems coming up with this algorithm, Steepest Descent. And before I go and show you any demo or anything, let me talk about them, because that's quite important. So there are three major problems with this Steepest Descent idea. One of them is, and the most important one, is local extrema, in this case local minimum. So let's say you start here on this surface, which is kind of like the MATLAB surface, and you want to end up at the what? At the global minimum, right? So the point that you really hope you can end up is this point here. This is where you want to end up. This point in black is where you are starting. Fine. What do you do here? You move in the negative gradient direction, and it brings you, let's say, to this point. Here, you calculate another negative gradient. It brings you here, and then it brings you here, and you find yourself ending up here. Now, when you are here at this local minimum, which is small, which is bigger than the global minimum, so this is your global min, this is what? Your local min. Your goal is to end up at the global min, but if there are these smaller sinks, smaller in terms of size, of course, minima, then you might end up at those, and when you get to those, since they are also stationary, the gradient at those points is also zero, and that means you're not going to move from that point any further. So both at local and global minima, at both of these guys, del f is 0. And when del f is 0 vector, based on what we know here, what's going to happen? When del f is 0, correct, this whole term becomes 0, so your next point and your current point are going to be the same, and that keeps repeating itself, so you're not going to move. And we call it, you're being trapped. We say you are trapped in a local minima, and you cannot get out of there and go to the global minimum. That's the most common problem, and it happens if your surface is not a simple function like this. Okay, when your surface that you are optimizing, your function that you're optimizing, especially the more variables you have and the more random parameters that come into play, it makes these uphills and downhills more and more. You're not going to have a nice surface like this that has one big global minimum and nothing else. So wherever you start, you end up here. No. So in these problems, it's a good idea to be a little bit more conservative and don't move fast. If you don't move fast, you have a chance that when you move and come, let's say, to this point, instead of all the way down, if you just come here, maybe the gradient can help you what? Maybe the gradient can help you steer a little bit away from that direction and then keep going what? In this direction. There is no guarantee, but many times it's like walking in a dark room, right? When you're walking in a dark room, when you're walking in somewhere with so many pitfalls, with so many traps, it's better to move a little bit slowly but surely instead of moving fast and not being careful. Okay, so that directly goes to the third issue. How do we choose the step size? Big step size hopefully gives us faster convergence to the global minimum, but it can decelerate the convergence. Smaller might take a little bit more. It can help. So how you choose the step size, specifically when you don't have an analytic function like this. There is no direct analytic relation like this, because if there is, I'll show you, you can analytically find a good answer for the step size. I'll show you for this function. If you're given an analytic function, finding the right step size is not that hard. But if there is no function, you just have some numerical values, that's all you have between these variables and your objective function, then you have to decide on the step size. And one of the things that some people do, they keep changing the size of the step size, okay? They might go large and then try to change it to smaller and smaller based on the amount of motion that they will get. And the other problem that comes into play then is the flat planes, areas like this. If you start on a flat plane like this point or this point, what's going to happen? Well, it's flat. The gradient here is 0. Slope x and slope y, they're both 0. So here, the gradient is also 0. Although it's not even a local minimum or global minimum, on these flat planes, there is what? There is 0 derivative, which means you're not going to move. So if you start there, you're going to stay there forever. And that is another problem. If your function has not changed a little bit, then maybe you are trapped on a flat plane. So in those cases, you have to do something to help this method. Random motions or other algorithms like Levenberg-Marquardt, which we're going to discuss in a separate video, come into play to help with this steepest descent and make it converge, hopefully. Okay, so there should be some tweaks or modifications to this steepest descent when there is no analytic function and some criteria of how you choose the step size. Again, we're going to see such algorithm, which is called Levenberg-Marquardt. We're going to see that in a separate video. But here, we just assume, for the sake of this simple lecture, that there is an analytic function that you want to optimize. Well, because if there is an analytic, it's not even, you don't even need really an optimizer like that. All you need is to what? All you need is when I'm given a function like this and somebody says, okay, what's the minimum of this function? What would you do? If this is z from your calculus, you know that you come here and you say partial derivative of z with respect to x is 0, which in this case is 2x1. x1 is 0, and then partial derivative of z with respect to x2, which in this case it is 6x2 is 0. So you clearly see your global minimum is 0 and 0 here, right? And then you check it for whether it's a max, a min, or a saddle point using the second derivatives, correct? You know the test for a point being minimum, maximum, or saddle point, right? You know first and second derivative tests. So I'm not going to go into calculus, but hopefully you know that. In this case, you can clearly see that this function is having a minimum at 0.0 and 0. Fine, so I don't need any iterative loop. I can directly use my calculus. So the only reason I'm using an analytic function here is because I want to demonstrate that this method works. Okay, I want to show you the contour plots and everything and show you that this is working, right? And the goal is not really to say that this is all this method can do. No. So if I have an analytic function like this, what should I do? I start at a point that I want. At the point, I calculate this negative gradient, I move with the step size of a in that direction, get to the new point, recalculate gradient, negative gradient, move until my function is not decreasing anymore, and then hopefully I can call it the global minimum. So two things you need. One is the gradient vector, which is definitely the vector of partial derivatives. So this is that gradient vector of f that you need. Correct? At each point you have to calculate this vector. The other thing is, what should I choose for a? In this case, I'll show you that you can really analytically determine what's the best a to choose. There is a way to determine that. How? Well, as I told you, the location of the new point is going to be a function of what? A function of this step size, right? Now, what do? If the new point is a function of the step size, I'm going to plug this new point into my function. It has x1 and x2, both of them function of a in general. It gives me this f of x or f of z. It's going to give me a what? It's going to give me because it's a scalar value, right? You plug the components here, it gives you a scalar value, and that the scalar value is a function of a. And that the scalar value, I call it what? G of a. Now, how much of a do I choose? I choose an a that gives the minimum of this function f, correct? Or g of a. So basically, I choose an a such that g prime at a is equal to 0, because if that's 0, it means g with respect to a is going to be minimum. So all I need is, again, plug a into the update equation, which is this guy. Plug the new point coordinate into my function to get this scalar function and set the derivative of that with respect to a to 0. That gives you the optimal value for a to choose at any point. Let me apply that to this example so you can see how I find that for you. So in this case, my f is x1 squared plus 2, or 3 actually, right? It is 3x2 squared. Now, del of f, as we just saw it, it is equal to 2x1 and 6x2. Now, z, the coordinate of the new point, is equal to whatever was the coordinate of the previous point minus a times del f, correct? So it is going to be what? It is going to be x1 and x2, the original point, minus a times what? 2x1 and 6x2 at that very same point. So your z of a is going to be what? If you add these two vectors together, it's going to be x1 times 1 minus 2a and x2 times 1 minus 6a. Correct? I just factored out here when I added them x1 and x2. Now that I have this z of a, I'm going to plug it into the f function. So this guy here is going to be plugged into f. And if you do so, then g of a, which is equal to f at z of a, is going to be what? Is going to be this guy here that goes and sits instead of x1. So it's going to be x1 times 1 minus 2a, the whole thing squared, plus 3 times x2, which is now x2 times 1 minus 6a, the whole thing squared. Okay, so clearly see this g of a, it is a function of a, and now you have to basically take the derivative of g with respect to a and set it equal to 0. So g prime of a is what? So here you treat x1 and x2 as two given numbers, as constants. So what you really need here is to take derivative of 1 minus 2a squared, and x1 squared, again, you treat it as a number. So it is going to be what? 1 minus 2a, the whole thing squared, is going to be negative 2 times 1 minus 2a, that's the derivative of the a term, and then times x1 squared. And here you have plus 3 times, this is going to be negative 6 times 1 minus 6a, and then times x2 squared. This whole thing has to be equal to 0, and if you factor out a and take the non-a terms to the other side, what will you get? So here you have a positive 4a times x1 squared, and then here you have 36 times 3, correct? 36 times 3, which is 108. Let's make sure we are not making mistakes. No. So it is 108 x2 squared. This is equal to 2x1 squared, and then 3618 x2 squared. Okay, that's what we have. Now I would go ahead and simplify a 2 from each side. And if I calculate a, you see a is going to be x1 squared plus 9x2 squared divided by 2x1 squared plus 54x2 squared. So at any point x1 and x2, if you use this formula to calculate a, that ensures what? It ensures that in that direction that you just have, in this direction, you go as far as what? As far as you can to decrease the function, right? Because if I go ahead and slice this function, this 3D surface, which I have the contour plot of it, along this direction of negative gradient, if I bring a plane and along this plane, I go ahead and cut the surface, right? If I cut that surface with this plane, this is the top view, the intersection curve will look something like this, which is basically what? You are here right now, and you can go down, down, down until you get to point x1, and x1 is here. Once you pass x1 on this plane and let's say end up here at this point, x1 in green, x1 alternative, then you end up here. Okay, this one maybe I can call it x1 star. And this point I can call x0. You see, so when I move in that negative gradient direction, my function decreases, decreases, decreases until somewhere after that it starts to increase, right? So it's best that I keep moving until I get the minimal value that I can, then I don't proceed anymore. Now I reevaluate my gradient and I move in that direction until I get the minimum of it along that direction. Once I pass this direction after this x2 and come here, again, my function is more than what it was at x2. So I should stop at x2, reevaluate, and keep going. So if I do it this way, it ensures that in each direction I go as much as it reduces the function, then reevaluate. Now, if I choose a different step size than what I have through this formula, then what's going to happen? As I told you, instead of ending at this x1 squared, I will end up at here. So I will end up here. I stop prematurely, and I have to reevaluate and reevaluate and reevaluate, and that makes my convergence slower. I need more iterations to make it happen, right? And if I choose a big step size, so I end up at this point x1 in green, that's a huge step size, so it's this much compared to this much. Then I will pass the minimum point, and again I overshoot where I should stop, and again that leads to more iterations. So the ideal case is I stop at this x1 star. In this case, I can find how much step size I need at any point through this analytic formula. So if I can plug this guy into this update equation, right, times A, if I can plug this A, then that makes my convergence the fastest. The problem is, many times I do not even have this function f, analytic function. All I have is a bunch of x1, x2 values and a bunch of f values. That's all I have. There is no function to take derivative like this, plug in, take derivative, and then find the optimal value for a. In those cases, you have to decide on something about the step size. Okay, and that makes your convergence a little bit slower. So let me show you all of this in a MATLAB demo. So here, I have this function for you, and I calculated the components of the del or the gradient, and I have my optimizer to run at max 100 iterations. If it doesn't converge in 100 iterations, I would stop the loop. And I want the change in my function to be less than 10 to the negative 3, so I claim it to be converging. In other words, if the value of f, this function, at the current iteration minus the value of f at the previous iteration is bigger than this threshold, I still let it move because it's still moving. If it's moving less than this amount, this small value, it means you are almost at the stationary point. So you better stop, right? So here I'm starting my optimizer location at the start point of 4 and 4. You can choose whatever point that you want. And then as long as my conditions are valid and I have not converged yet, I keep updating my a value based on the formula we derived. I calculate my a times gradient with the negative sign, negative gradient times a, or the amount of movement basically. And I add it to x1 and x2. I also calculate the amount of change in the function to use it here and see whether I have converged or not. And here I plot the contour of the function and I show on it the optimizer at different locations and the line of the gradient at those points, as well as the value of a. I draw the line of gradient at each point with the magnitude of a. Okay, so when the length of the line decreases means the amount of motion is decreasing and I'm getting closer and closer. So take a look here. So I start here, I move in that direction, this much, this much, this much, and boom, I have converged. If you look at my II, you see it only took 7 iterations. Actually 6, because the first point is the initial point. So it really took 6 iterations for me to converge from initial point to the goal point, right? The global minimum. And you see, as you get closer and closer, the size of that black line, which is the gradient direction with magnitude A, is reduced until when I get here, it's almost at 0, and my function is at the minimum, right? So this is the demo of it when A can be analytically calculated. Now, not always, as I said, A can be calculated analytically. So here, let's go ahead and instead of this analytic formula for A, let's decide a number for A. Okay, so let's choose something for A and say, hey, maybe I want my A to be 0.5. Okay, wherever I want to use a step size, use 0.5, and so I'm not going to calculate it anywhere. I'm just going to take it as 0.5, right? Let's see what happens. There we go. Even got trapped. You're not changing anymore. Okay, and it should really, you see, let me look at the final values. A is 0.5, and each direction I move by A only. Good. Let me make it a little bit smaller. Run it again. Okay, that was better. At least it converged, and it took 12 iterations. So you see, I used 0.1. It took me, what? 12 iterations to converge. Now, if I want to be a little bit more conservative, I change it to 0.1 and run it again, taking smaller steps. It is converging again, but definitely at more iterations, more time. There we go. So now it took 22 iterations, right? Now somebody might say, well, why don't I go with let's say 3? Let's go faster. Sure, you might. You might, right? You see, you're doing overshoot each time. So it costs you more, actually, iterations. Although you're taking bigger steps, but look, although I'm taking bigger steps, it took me 24 iterations, while with 0.1, it only took me 22 iterations. With 0.2, it took me 12 iterations, right? So choosing the right step size, with some of them, I might overshoot so much, like 0.5 I showed you, that I don't even converge. So choosing the right step size and how to change it per iteration of the loop is a very important thing, because as I said, you do not really always have this analytic function and this analytic formula for A. If you do, yes, that guarantees the fastest convergence possible, minimum number of iterations. But the matter of fact is you do not have such a thing at hand. So we're going to talk in the next lecture about how to choose proper step size and how to modify the steepest or gradient descent algorithm to take care of the problems it has, like, as I said, flat planes, local minima, and the proper way to change the step size. Thank you so much. I will see you in my next video. And please, as always, share the videos with your friends, with whoever is unaware of this channel, and please subscribe to the channel. Thank you so much.